All right, so now, this is basically putting it all together. Okay, we're going to get that action potential. That action potential, now I haven't gotten into the nerve yet, but they're showing you the calcium that helps to make the nerve work. Okay, that action potential makes the neurotransmitter get released. The neurotransmitter's release, in this case, acetylcholine, attaches to the ligand gated. Ligand gated opens, sodium rushes in. We can now have that action potential pass along that muscle fiber. It will affect the voltage gated. As that action potential moves down the fiber, this sarcoplasmic reticulum contains the calcium. Calcium gets released. Calcium attaches to the troponin. Troponin twists or moves the tropomyosin. Myosin heads, as long as ATP is present, can attach to the active site and pull that thin filament towards the midline. Let's say, for example, that we get all of the process where we've gotten the action potential, but there's no calcium, or the calcium is low. What could happen in the rest of this process? If the calcium was low or not present, it wouldn't do any contraction, because we wouldn't have the attachment to the troponin to move the tropomyosin to make the active site available for the myosin head to attach and create the slide. Does that make sense? Let's say we got the action potential, but there's not enough sodium. At what point could the process go wrong? Think about the very first part where we're dependent on the movement of sodium. At what point, if sodium levels were low, would we have issues starting with the nerve? Well, the nerve transmission came in, but we have low sodium. At what point would we see a problem? We would ligand, because sodium, that's the first place that the sodium will rush in. So if sodium is low, we don't have enough movement of the sodium. So the muscle is getting this nerve signal, but reaction is low. So do you see how now the ions, the sodium, the calcium, now the potassium? So, where does potassium come into play? Plasma membrane, the voltage, hey, don't worry about it, I get that all the time. The voltage back to what? To the rest. See how cool it is? Isn't it cool now? Yes, Dr. Young, it's pretty cool. Okay, good. So here's what will happen. Once the muscle contracts, the goal is that hopefully that muscle is going to relax. So for the muscle relaxation to occur, we're going to see that we're going to need a little more energy, because we need to move that calcium back into that sarcoplasmic reticulum, which means probably under normal conditions, we've got to move it against a concentration gradient. So we need some energy to move that calcium back into those little cisternae. That means calcium pulls away from the troponin. So the troponin tropomyosin complex is going to now shift again. And when that shifts, it covers back up those binding sites on the actin. And therefore, the binding sites are no longer available. If they're not available, myosin heads can't attach. Pretty cool. That's all we need to know for relaxation. So, going back to thinking about this voltage, okay? Thinking about that nerve meeting that muscle fiber, changing that voltage, and then being able to get to threshold. Because that's the thing. If we get to threshold, okay, that muscle will contract no matter what. So, the way that it is studied, okay, the way that we know what's happening, we focused on what takes place in one fiber. Because if you can figure that out, you kind of have an idea of what's happening in all the fibers. So, we say that we get a muscle twitch. Okay, come on guys. When you hear the term muscle twitch, is that probably what you're thinking about? Okay? Or, all right, something like that? A little different, okay? Because we're going to now think about it on one fiber, okay? Now, when we get a muscle twitch, hopefully at this point, I've pointed out so much that a contraction has the stimulus from the nerve. All right, that's kind of like you're thinking, please don't tell me that anymore. All right, now in one or more fibers. So we're going to have it in phases, because when that nerve meets that muscle and we get the action potential, can everything happen along that fiber at one time? No. Remember how we said it had to propagate? Okay? So, when we get that stimulus from the nerve to the muscle fiber, we're going to say that we have a lag phase, we have a contraction phase, and then we have a relaxation phase. Now, they're trying to show us in time, okay, the length that these phases last. So, we come over here, we get the stimulus. The lag phase is the shortest. So that stimulus has arrived. We have now gotten some voltage changes that are taking place. Now, contraction phase, just a tad bit longer than the lag phase. Good grief. Look at relaxation. God, it seems to me we'd mostly just be going around and be like, all right? But that's not how it works. Mainly because time is basically milliseconds for this to occur. Milliseconds. When we begin to look at the structure where we're going to find the big nerve enter the muscle, begin to branch and branch and branch and branch until we end up with these little terminal buds, okay, meeting their own fiber, their fiber, their fiber, their fiber, okay? When we've got that taking place and we begin to look at the structure that's getting formed and the branching meeting every little single fiber, where we get that nerve meeting a fiber, the point where they're going to meet, okay, we call it a motor unit. Now, we'll stop right there and explain something. Even though we're not going to really hit this, okay, until the next chapter and then in part 2. What does the term motor mean to you? Running, it's movement. Okay? I think about the motor in my car, and it makes my car go. That's telling me I get movement. Think about the structure that we're dealing with here. We're dealing with skeletal muscle. The job of skeletal muscle is to make us do what? Move. All right? Whether it's writing on the paper, whether it's walking, whether it's sitting, whether it's standing, whether it's laying, whether it's breathing, whatever the case might be, skeletal muscle is about movement. Therefore, the term motor. The other term that we're going to have to deal with, sensory. Which part of this makeup do you now think is the sensory portion? Because I'm looking at the connection of my nerve to the muscle. Which part is now going to be, that we're going to look at as being the sensory? Which one? The muscle or the nerve? Muscle is our motor. The nerve is now going to be considered sensory. Okay? Just put that in the back of your mind. Because the first time you see motor unit, you're probably thinking, why are they terming it motor? Okay? Well, the reason they term it motor is because it results in an action. All right? And that comes from the muscle. So therefore, the motor unit. So, we're going to say that we have numbers of these. I mean, hello. Look at the numbers of, I don't even want to know how many. If I've got 600 muscles, I don't even want to know how many fibers I have, much less the number of little nerve endings that have got to meet those fibers. Okay, I probably wouldn't understand that number. Would I like to have it in dollar bills? Of course. Okay, but I don't. All right, so that number is huge. Is everybody kind of following me? If we have a large muscle, think about the quads, think about the biceps, think about the deltoid, think about the biceps, okay? Do you see what I mean by big? Okay, a large muscle, usually we're going to have a lot of muscle fibers that can be present, so therefore quite a few motor units. If we have a small muscle, usually there are less fibers, the function is more fine-tuned, and we're getting maybe less units. But wait a minute, what is going to be my purpose of the motor unit anyway? All right, why?